Thanks, Vikash. Thanks, everyone, for joining. Thanks for the opportunity to participate in this extraordinary event. We are very honored and pleasured by this opportunity to share a bit of our research work implementing in Python HL with PyMeasure and TestStand. Before we start into the topic, let us recognize one of our giants at the university, FH JOANNEUM, which is Birgit Dorner. She is both Gabriel and I know very well, very engaged and extraordinary person, always coordinating and communicating with lecturers, students, aligning courses, schedules, even if things are shifting. Always very positive, very kind, very friendly, and this is what we would like to recognize throughout also this presentation, which we really appreciate. All right, jumping into the topic, we're going to first introduce ourselves, then we take a look at the agenda, and then I will start with a little bit of an intro on the university and the background and the goal of it, and then Gabriel will dive into the PyMeasure and the abstraction stuff. There we go. So, as you might know, my name is Wolfgang Rominger. I'm working for NXP as an architect for automated validation since a couple of years now, which is my full-time job. And since 2019, I joined a new master curriculum program called System Test Engineering as a part-time lecturer for software environments and programming and test and automation laboratory. And I gained some certifications along this way. Anyway, I also would like to introduce Gabriel, and that is what he's going to do himself.
Thank you. So I'm a student of Wolfgang at this new master course, which I am, of course, currently a student of. Basically, what we learn there is how to design tests, how to test software, how to test things in the automotive industry or semiconductors, and of course, how to automate these tests. And previously, I was doing the bachelor's degree of electronics and computer engineering, which is where this thesis I will be presenting was done at. And there we did some circuitry and programming of microcontrollers. And I also had the chance to spend half a year in Canada, where I also mainly programmed microcontrollers. But now I think we'll get into the topic started by Wolfgang.
Absolutely. Thanks, Gabriel. So the outline we prepared for today, a little bit of background about this new master curriculum, system test engineering, then the architecture that I had in mind, or I have in mind, it's still a work in progress thing, how to deal there with virtual environments and the test and integration. And then we're taking a closer look on how it is implemented. And this is, of course, not written in stone. This is still developing and also not yet completely finished. It's more a starting point for the seminars and courses there. All right, so the FH JOANNEUM, University of Applied Science, is located in Austria. Consists of 3 sites. There are more than 5,000 students, which I learned today, over 7 departments and 50 different studies, either bachelor or master or postgraduate programs. And the system test engineering master degree program is pretty new and part of the electronics and engineering department. And it was co-funded with several industry leaders in semiconductor and automotive industry back in 2019 to have and develop the skill set that is needed for systematic testing of complex electronic and mechatronic systems. It's a 4-semester program. There are 16 to 20 places available. It's in English, and I think there are not many programs like this. The outline of it is just in a nutshell divided into different sections, where software engineering is one part, also electronics, but requirements gathering. So those kind of topics that are needed in the near industry is taught there and shared with also people from the industry teaching there, also from Infineon, Austro Microsystems, AVL, Magna, and NXP. And those two lectures I'm responsible are one in the first semester and the other one in the second semester, which Gabriel briefly touched with software environment and programming and test and automation laboratory. Where in the first semester, the basics are taken to be able to run automated test sequence then in the second semester on characterizing an ADC. It is obvious that due to my background in LabVIEW, I tend to do that in LabVIEW, but it's also kind of required to do their text-based programming, and it's also more appreciated by the students, I think. There's a sneak preview of the lab that we have for automation and test. There are PXI systems on several benches. There with digitizers, function generators, a digital pattern instrument, a multimeter, power supply, and SMU, which is very useful for mixed signal measurements. And of course, in a similar way, equipped with benchtop instruments that can be remote controlled. And this is kind of also the target bench with which the students are working usually. So the goals set for the project that Gabriel was doing in collaboration with me is I wanted to have something that is a Python library for also controlling instruments in an abstract way, similar to those hardware abstraction layers that are available in LabVIEW. To be able to do automation exercises, simple ones, since the methodology doesn't differ too much from a simple task towards a complex task. It's always the same methodology that is used if you either characterize an NFC IC or diodes or filters or ADCs. And therefore, instrument control is a key part. And there are already libraries for LabVIEW that students can use, but nothing for Python. And keeping in mind modularity and reusability to be able to switch seamlessly between benchtop and PXI instruments. So this is one very simple example of the first semester where students get the task to automate the capturing of Bode plot from a bandpass filter or any other filter, and they just completely automated by running a test and sequence calling LabVIEW steps at the moment, and this is the goal, or was the goal, to replace them or to be able to do that also with Python in a similar way. So the concept and architecture, I think you all know or have seen this picture before. We follow the same approach, since this seems to be also widely accepted in the industry, that there is on the top layer a sequencer with NI TestStand, and then there are code modules developed in any kind of software interacting with instrument drivers, which are in the end interacting with instrumentation and performing the interaction. For today, we're just going to focus on other software and a little bit on TestStand, not so much on the instrument driver and on the instrument itself. So diving into, I think this one, I wanted to explain there a little bit why I tend to follow a modular approach and also not run away with, okay, there is we have a scope, we have a benchtop instrument, and we know the Skippy commands, and then we just start implementing. We thought it through and came up with a more modular concept where we wanted to spend some effort initially, and which scales then better depending on the complexity, because with the same libraries, it's possible to do filter measurement automation as ADC measurement automation as any kind of other measurements, because we could just add libraries on top, where if we would have just run away and started developing one Python script without thinking of its modularity and how to set it up properly, we most likely would end up in a big mess. This is what I like to refer to the automation onion. The closer you go from the outside into the inside, the more you start crying. The TestStand wrapper for sequences, then some abstraction for the instrument categories, the PyMeasure for benchtop instruments, and the NI libraries for the PXI instruments, and the Visa driver in its core for the benchtop instrument control. Going one step further, I think in HAL, I might not need to explain to anyone anymore on the very top level, and Gabriel will show the detailed UML diagram with the class hierarchy and the involved members. On the base, we have an instrument class with some generic properties. Then we have derived from that the power supply, oscilloscope, function generator, and multimeter class. And then for the different vendors, the specific implementations, and for the Keysight and TTI implementations, we are using PyMeasure, and for the others, the NI, the available libraries from NI for the PXI instruments. How does this look like now from top down, from the TestStand perspective, semantically zooming closer into the code modules that Gabriel developed? So the workflow, as I think is the simplest for the students, is to have some templates here on the right, which are functions that can be dragged and dropped and are subsequence calls, and are parameterized here in the step settings down here, where a reference to the instrument is given, to the instrument configuration is given, and then variables are set for the configuration. And this is, by the way, already a real-world example of an execution for automating the measurements of a bow diploid. So let's take a closer look inside this shared sequence function generator.seq and take a look where the Python modules are called. So what you can see here, that this is just a wrapper to wrap the Python code or any other code, since the interface of sequences will most likely stay the same. The ones from the adapter configurations might not. And that's why it's wrapped into subsequence. Every single function, every operation that can be executed in an instrument is also here in a way possible to remote control. And what we see here is a way to create the object reference to a function generator in this case, where there is this init instrument step. There's some housekeeping up here to select the proper type. The configuration for the instrument is reference is coming here from the parameters, deciding which type should be instantiated from the object-oriented hierarchy in the background. And here you see also not very new to anyone, I guess, the Python adapter with the configuration of the Python script and which method should be called. In this case, it's create instrument by channel. And these are the parameters here, and this is then the return value, and the return value is stored back to the parameters, and this is then the only thing that is needed for all of these subsequence calls to be interacting with a certain instrument, giving the object reference to also the other Python steps. Yeah, what is important to mention is that the type here is really mandatory to be configured for most of those variables. Otherwise, you might get runtime errors. And this is the underlying Python factory that is called. And it's, as you can see, and you will see later, importing all the existing libraries at this moment. It's specifying some enumerator classes for the supported instrument types and vendors. And down here is this method create instrument by channel, where the instrument type is provided, the vendor is provided, the resource string and the channel name. And then based on that, very simplistically here, a dictionary was created, and it's based on instrument type, vendor, the proper constructor and class and object reference is returned. And this is done in a way where we have set up also a virtual environment. For those that are familiar with Python, they will also recognize this concept. It's a way to isolate different Python versions on a single machine, have different environments, handle multiple different Python versions, also manage dependencies much better because you can only install dependencies for certain projects in this virtual environment. It's easy to set up. It's just requiring a pip, which is called virtual env. And then when you run it in the command line interface and specify the name to the directory where you want to have it, it auto-populates and creates the necessary content. And to work with it, the activation script needs to be executed. And in TestStand, it's even easier to use that virtual environment because with the adapter configuration for the Python adapter, you can specify just the path to the virtual environment, and then it will run all the Python steps unless you specify it in the steps itself with this environment and this configuration. And this becomes very, very handy for setting it up in a simple way. Right, and I think with that, I would like to hand it over to Gabriel. If you want, you can request control or you ask me to move to the next slide.
Thank you. I think it should be quite clear when I'm moving on to the next point. So let's just try having you switch over. So to start with the first slide, as Wolfgang already said, most of you are probably familiar with the overall structure of an HAL, but I will just quickly introduce what I did here. As you can see, the structure that Wolfgang already mentioned is implemented by me, meaning at the very top we have an instrument class, which is just an overall class, for example, containing the resource of the instrument I want to use. And below that, in the blue square, we have our 4 different types. That would be a power supply, a multimeter, and so on, which are already a bit more specialized. And below that, I have then an implementation of a specific vendor of the type of measurement instrument, which then implements the instrument that I want. Below that, I have PyMeasure and NI measurement instruments, which are libraries that I'm using. I will come to that later, but they are quite the big part in the actual implementation of how I communicate with instruments. But first, I really want to start with the 4 kind of overarching measurement types, which would be power supply, multimeter, scope, and frequency generator. I think for the most part, I will stick with multimeter as my example, but I'll just start here for a second. So as you might be able to see, those 4 names are italic, meaning it's an abstract class in Python, which means I usually never create any object of that type. The object is always of the type below, but I have all the necessary methods in this class, which I can then later call, which is why those 4 are really important in TestStand, as Wolfgang showed you, because that's where I can call those methods, but the implementation of one of the child classes is then called, which is the whole idea, of course, of an HAL, and it's implemented quite nicely here, I think. Then if you move down, basically once we have the implementation, for example, here DMM Keysight, which would be my implementation of how to communicate with a multimeter from Keysight, and it is in a composition with PyMeasure. Reason being that basically all the Skippy commands and things like that I do send are done by the PyMeasure library, meaning I create an object within PyMeasure, and that's where I then do my communication mainly. that's really practical, as I will show later, because in that way I can use the power of the many libraries available in Python. One last thing on that slide would be the factory and logger at the very top. The factory was already explained by Wolfgang, and the logger is just a handy tool I developed because sometimes if you call a Python method within TestStand, it can be quite hard to find the bug or what was called. And with a logger in place, it's just really easy to then backtrack of what could have gone wrong. So it's mainly a debugging tool, this logger. And yeah, that's the overview, and the folder structure which I've developed is on the side, which is of course really similar to the HAL structure I just mentioned. Now going one step further, going in, I will go on with my DMM example. So as mentioned, the multimeter itself is abstract, which is why basically it's just written out in this picture here. And below that, I really have measurement equipment. I think that just illustrates quite well how the abstraction works, and that I then later can call functions within multimeter, which then really do something in the implementation below. The idea of that is that I can automate my measurements even through a change of device with the TestStand sequence by Wolfgang. Meaning if I, for example, would change laboratory and suddenly, instead of a PXIe DMM, I only have a Keysight multimeter, I can still call the same sequence and only change the resource name, for example, and my sequence would run through just fine, which is very handy if you, for example, would have to swap laboratories often at university. And yeah, that's the main point of it. And now I will go ahead and kind of explain some code for you to get a better idea. So what I did here is that I highlighted parts that basically have a similar job inside of my code. So for example, the thing in the red rectangle is always the implementation of the measure function for my DMM. Of course, as I mentioned, the multimeter overarching class itself is just abstract. That means I only raise a not implemented error if for some reason I would create an object of that class and try to call it. However, below that, there are implementations for it, and I think it just does a very good job of showing how different the implementation below is, but the result returned is still the same. Meaning, for example, that with the NI DMM, I of course have to start a session and then configure my measurement, and then finally can read out the measurement and return it. While if I do the same with Keysight, I don't have the whole session process we know from NI measurement equipment. There I can basically just go ahead and read out the value once it is instantiated. Coming to the initiation, that's basically the green rectangle. All I do is I call, or I create an object of a class, and the class in this case is always outside of my project, you could say. So for example, here, my object self.dmm is an object created by PyMeasure, which is the library I'm importing in the, thank you, in the blue rectangle. And the same happens with the creation of the session for the NI multimeter, which basically also goes ahead and uses the NI DMM library, and then creates for me an object, a session object in this case. So that's mainly the overall idea of it. And I think you can already tell it's quite handy that a vastly different implementation still can always be called for the same later in TestStand with just calling the parent class of Multimeter, and the user, which in this case will later be students years below me, can then just go ahead and call functions of the class Multimeter, and they don't have to bother with knowing how my implementation below looks for the actual measure function of the Keysight multimeter or of the NI DMM, which means they basically only have to work with TestStand if they want to develop the sequence. Okay, then moving on. I just quickly want to show one example of how PyMeasure could or does look. So we have the class of the multimeter I just basically implemented, so the HLN 34450A. And the interesting thing here is that it calls instrument as the parent class, so it is a child of instrument. But it's important here to not be confused. It's not my instrument class that is called or that is the parent here, but rather PyMeasure, of course, as a whole project also has an abstraction within it. And this instrument class here is different from mine. However, it has similar jobs. What this instrument here does is basically it opens up the skippy commands, and if adapters are needed, make sure that those are in place. So basically what it does, it starts the connection to the instrument for me in Python that then I can communicate quite easily with the instrument. And all that is already basically available in this open source project called PyMeasure. As you can see below, I put just two examples with current range and current auto range. This is how you kind of interact with your measurement instruments. Meaning basically all you do is you have this this attribute, and you just can assign a value to it, and it more or less automatically then gives the according skippy commands to your device and controls it via that, which results in a, from my point of view, very, very nice syntax if you are communicating within your code. If you want to set some values, it's just, from my point of view, very nice to work with it. And as you can also see, things like validators and which values are possible to set are already in place in most PyMeasure files, which of course also once again reduces the workload from us as developers to do that for every single instrument we want to use. So basically all we have to do is the very tiny implementation that I did, which was shown before. That's basically the how it is done, and I think you can also already tell that the skippy commands are just can be easily found here, which ties into my next point, which I will discuss on the next slide. It's the last point, easy to add and modify. So as you've just seen, it's quite easy to basically just change those skippy commands, which makes it really easy if you have a new instrument to just take any existing PyMeasure file and alter it slightly, and then suddenly have a completely implemented new device, which is what I, for example, did for our TTI power supply since it was not available. Basically, I just created a new file within PyMeasure and just took a template from a different power supply, and all you have to do is slightly alter the skippy commands that are being sent to match your device, and that's already it. And you have basically the library altered in a way that you can use all your devices again. You can, however, see on the right that there is already quite a huge library already implemented. For example, my Agilent multimeter I used could be easily found in here. And there are many vendors providing, or not the vendors usually provide it, but contributors provide files for the implementation of this PyMeasure for many different instruments. And yeah, there are many contributors, many devices already implemented. I think as far as I've seen on GitHub, it's quite well structured and managed. And I could not yet find really any bigger flaws within the code. So I think you can, with quite good faith, use things from this GitHub project. And yeah, the hierarchy within is also with an instrument behind it. But I think that's quite clear. And so yeah, the PyMeasure library is really powerful for us to implement benchtop instruments, which we then can call in TestStand. Okay, then as someone doing a thesis, I of course had some findings or learnings which I briefly want to add, starting with the logger, which after its implementation greatly helped me debug, because as I said, Python can be kind of hard to debug through TestStand because it's not always so easy to understand which function was called with which parameter. Another finding was that for those of you who are more familiar with Python, decorators exist, and you can basically tell a Python method that it should be abstract with add_abstract method. However, TestStand does not recognize this, and later then does not understand this is not implemented, and that it should call a child instead, basically. So that decorators are kind of not detected from what I've seen. And if you nest Python classes, we tried that with enumerators. They sadly are not accessible in TestStand as far as I could tell. So we had to take our enumerators and put them basically outside of our classes, which is no problem, but it's just important to know because that might be a roadblock for developers. The parameter types and tests, and Wolfgang already mentioned that you have to be really careful to make sure you get back the correct type, and it might cause problems if you just keep it on dynamic. So make sure to do that. And even when you put the enums outside of a class, it's still a bit trickier to operate than with enum you know from LabVIEW, because you basically have to make the enumerator again in TestStand, which I think has to be the same as in Python, and that way you can then use it, but it's just used a bit differently, I think, which is why it has extra workload. And yeah, that's findings I can give you, and Wolfgang, I think, has some more.
Yeah, I just want to add to the enumerators. At least we were not aware how to directly translate them to TestStand, because in Python they are classes and objects in the end. So that came to be a bit tricky. The other thing is that is more an, how to say, workflow thing. Is it makes in my opinion a lot of sense of wrapping the scripts into TestStand sequence files and subsequences, as I showed earlier, because interface changes are then handled on a central place. The other thing is if exchanging Python or LabVIEW modules underneath, it's also easier if you just have the same sequence file name, but a different content, for instance, and implementation of other adapters is easier. Yeah, so that's kind of what I think is worth mentioning. And maybe before opening the Q&A, also an outlook, what I think we still will do in the future with other projects. First, I think integrating Python unit testing also for the code modules that were developed. I think that we left a little bit out of the scope of this research. And the other thing is it will be really interesting to benchmark then the difference between Python HAL and LabVIEW HAL. Yeah, and that's it from our side. Very much appreciated to be presenting and sharing that. And now we're more than happy to answer any questions.
I think there are a couple of questions on the chat here. The questions start from, what unit test framework did you utilize for the Python side of Codebex, which you already answered, I think.
Yeah, we did not use any unit testing yet. I think Gabriel, we have another lecture in this master program where Gabriel is currently attending, where they use unit testing, and he can maybe elaborate which unit testing framework we are using there, or they are using there.
We haven't gotten to that point yet,
Okay.
but for as Wolfgang mentioned, for this basically for this bachelor thesis, it would have gone above scope to really go into detail with the testing. So that's why, kind of to just keep the size down for now, we did not go with any unit testing, but of course I'm aware that for a proper project that would have to be done. But yeah, for now there was no unit testing framework behind the whole project.
I was thinking of using PyTest for it, just to answer that question from Jesper. The other question, I think, is it possible to use TestStand engine inside Python? We did not investigate that yet. We were happy to be able to call the Python modules and see that working. So this call run state, I don't know if I think since this is part of a DLL, it might be possible, but I don't know, someone else from the community knows. We have not researched that yet. There was one thing I don't completely get is where we typed from Jürgen, where we typed Skippy commands for the whole stuff over serial board interface. Okay.
Oh,
that was
this was just another other thing here. It was, we are feeling back in the classroom at university and so on.
Okay.
So it's pretty fine. When we at university, we have not used TestStand. We used the hyperterminal.
Oh yeah,
So,
using a terminal.
Okay, so thank you very much.
Must have been more fun.
Yeah, it was fun.
Did I miss out any other questions, or were there new ones?
So in terms of which versions of Python and TestStand are you using for this?
Since we started it last year, we started with TestStand 2019 and Python 3.9. 3.9,
okay.
I saw there Jesper was commenting that TestStand 2020 can transfer TestStand objects to Python. So should be possible then with TestStand 2020.
And is there any plans to share the other abstraction layer with the community at any point?
I was expecting the question. I need to think of it because I also want to make it part of exercises where people need to develop certain parts of it. So I'm not sure if I want to make everything public available that they just can copy paste it.
Makes sense, yes.
But I need to think of it.
Yeah,
I think it's still something that is maybe shareable, but not in the near future, since there's still a few we need to do our homework with that.
Yeah, sure. Okay, but no, thank you very much for that. That was really useful.
Thanks a lot, and also big thanks to Gabriel who helped me with preparing the content. Very much appreciated.
Yeah, thanks, Gabriel.